Okay, we're now recording. And try to share the screen here. All right. Now, full disclosure already, it's in my best interest to actually finish earlier tonight. I've got a pretty heavy day tomorrow. Okay, so I'm going to try to finish early, but I'll still try to cover everything I need to cover, which is 14.7 and 14.8. Okay, quick reminder for 14.7, skip problem 17. I kind of botched that up last time anyway. Okay, so let's throw out problem 17. So calendar-wise, I think I'm still going to be okay. Okay. By the way, 14.8 looks like it isn't that long, and it actually isn't that long. Okay, so it looks like a short assignment. It is. Okay, so I left off at 17, skip 17. 31 to 37 are kind of longish, but I'll help you through that. A couple of word problems, then 14.8. So that was my goal for today. So where are we? We are here. So the new adjusted calendar, 14.7, 14.8. If I can do this, which I think I'll be able to with plenty of time to spare. Okay. And I don't think I need to go on to another day for that. I should be able to finish everything today. If not, I'm just going to declare I'll stop, but I think I can do that. Okay. So that being the case, I will get started with the next chapter, chapter 15, but we're aiming for the chapter 14 exam on Thursday, the 18th, a week from Thursday. Okay, and you will have the entire class period for that. Okay, so we won't have any questions and answers. So if you have any questions, bring it up on Tuesday, 3/16. Okay, so I'll lecture as usual, first half, then maybe the second half, I'll let you ask questions pertaining to the test, pertaining to this material. Okay, so that's the way it'll work. So when we start class right away, on Thursday, the 18th at 6:10, I'll immediately send through Canvas announcements the exam. There won't be any lecture at all. You'll just have the entire period to do the problem. So if you finish early, then just leave, and that's pretty much about it. And again, I'm leaning toward that for exam 4 and exam 5. I think I can do that the way things are going right now. I'm slightly ahead. So we'll see how it goes. Okay, let me check the chat. So yes, roughly 10 questions still. They're just longer. Okay, so yeah, let me type some. Okay, right, now for today, I might be aiming toward this. It may be the situation where I'll go a little bit longer than the break today. So I'm trying to make it so there basically there is no break. So I could say break at the usual time and then go on for another 15, 20 minutes. Or if you don't mind, if you can just hang in there a little bit longer, I'll just get it over with and then that's it. So the break is we go home. Okay. So that's what I'm sort of aiming for today. Okay. Now, well, that being the case, I may not be able to answer so many questions. I don't want to totally, cut you out of any questions, but I may not be willing to take lots of questions. Okay. I still got, more days for questions and answers Thursday and next Tuesday, I guess, but maybe not so much today. Okay. Hard questions on the test, well, that's subjective. I'll try to make it so, the super long ones don't get done. There has to be some long ones, as you already know. Some of them are going to be cut along, but, we'll see how it goes from there. Okay. All right, so let's try to get started. I'll play it by ear. If I think we need to break, we'll break. But if it gets to the point where, okay, if I break or if we only need another 10, 15 minutes, if you can just hang on and let me go through that, then we'll just finish it all today and go from there. Okay. So the hard problems from here. So I was done with the quote unquote easier problems, the ones that involve the D and so forth. So now the 31 to 37 type. Okay, so let's take a look at those. Whoops. Knock this off. Okay. Okay. All right, so again, skip 17. We are now to these longer problems. Page 966. To find the absolute max and min of a continuous function on a closed bounded set D. And all the problems that we do are like that. Find the values of f at the critical points. Find the extreme values on the boundary. The largest of these is the maximum. The smallest of these is the minimum. Okay, and as I mentioned last time, the analogy back in Calc 1 was when you had a closed interval, you were trying to maximize or minimize on a closed interval, right? You took the derivative, set it equal to 0, but you had to check the two endpoints because the maximum or minimum might be at the boundary, the endpoints. In this particular case, the boundary is more than just 2 points, it's an entire function. Okay, so that usually takes up the most amount of time for doing these problems. Okay, all right, so that's 31, 33, 35, 37. I think there's 4 of them, and my goal is to show you maybe 3 of them. Okay, so 31, 37, find the absolute max and min on the set D. Now for these problems, you don't have to do the capital D, the second derivatives test and all that, because you just find critical numbers. So what are critical numbers? Set fx and fy equal to 0. That's good enough, keep it in the list. And then we analyze the boundary, which is the hardest part. Okay, so let's go 31. F of xy is x squared plus y squared minus 2x. D is a closed triangular region with vertices 2, 0, 0, 2, and 0, negative 2. Okay, so I started that last time just to illustrate. So we have a closed and bounded set. This is a bounded region. That's kind of like in Calc 1 where you just check the two endpoints. Okay, now you in Calc 1 took the derivative equal to 0. That maybe gives you a max and min, but again, you have to check the two endpoints because the max and min might be at the endpoints. So here, I find the critical points. That's easy. Find fx and fy, set them equal to 0. No need to find the d like last time, right? The d, put the d on your formula sheet. So fxx, fyy minus fxy squared, right? The harder part is to analyze this entire boundary. Okay. All right, and I showed you last time, the points they gave me were 0, 2, 2, 0, and 0, negative 2. I trust you can figure these out. This is x equals 0, going from negative 2 to 2. This is y equals x minus 2, from 0, negative 2 to 2, 0. And this is y equals negative x plus 2, or 2 minus x. Okay, so that's where I left you off last time. Okay, so critical points in the interior. So find fx, fy, set them equal to 0. So what's the derivative with respect to x? 2x minus 2. What's the derivative with respect to y? 2y. Okay, set them equal to 0. That's very easy. So 2x minus 2 equals 0, 2y equals 0. The only critical point is 1, 0. Okay, so 1, 0 is in the middle here somewhere. By the way, if the point is outside of that region, let's suppose I got 3, 0, I wouldn't even have to consider it, right? 3, 0 is not in my domain. So 1, 0. So what is the function value at 1, 0? So I just plug in 1, 0, 1 plus nothing minus 2 is negative 1. Okay, so the function value at 1, 0 is negative 1. So if you would, I can put right here, I know, let me change colors here. Z equals negative 1. Right there. Z equals negative 1 at the point 1, 0. Okay, that's the easy part. Now the hard part, analyze the boundary, of which there are 3 parts. X equals 0, y equals negative x plus 2, and y equals x minus 2. Okay, so I have 3 cases. Right, so let's analyze x equals 0 and y going from negative 2 to 2. So the analysis of the boundary, that's like in Calc 1 when they said find a max and min on the closed interval from 3 to 10, then you plug in 3, you plug in 10. This is the analogy, but it's not just 2 points, it's an entire boundary. Okay, so I have x equals 0 going from -2 to 2. Okay, so I just plug in x is 0. That's 0, that's 0. I have y squared, agreed? Again, x equals 0, put a 0 there, 0 there, the function is y squared. F of y is y squared, and we're going from -2 to 2. Okay, well, this one you can just look at it. If you're going from -2 to 2, the maximum is when I plug in either 2 or -2, that's 4. So the maximum is at 0 plus or minus 2, which is 4. The minimum is at 0. Okay. But if I plug in 0, 0, I get 0, which is not smaller than -1. So it's not a candidate for being the minimum. That's why I didn't bother to write it down. Okay, so one more time. At x equals 0. So x equals 0, I plug in 0, plug in 0. The function just becomes y squared from -2 to 2. So if I plug in 0, I get 0. The biggest it's ever going to be, we know the way the parabola works, it's going to be either at plus or minus 2, where I get 4. Okay, I can ignore the 0, okay, because 0 is not going to be either the maximum or minimum. So right now, the minimum is at 1, 0, -1, and the maximum is at 0 plus or minus 2 or 4. Okay, now I analyze along y equals x minus 2. See how long this gets. Okay, and x is going from 0 to 2. Okay, so y equals x minus 2. Let me raise it up. That means everywhere I see y, I put in x minus 2. So right there, put parentheses x minus 2. Looks like this. X squared plus x minus 2 squared minus 2x. Okay, clean up the algebra. F of x is no longer f of x and y, it's just f of x. So x squared plus x squared minus 4x plus 4 minus 2x. Clean up the algebra. X squared minus 6x plus 4. Okay, we know that's a parabola. So I can find max or min at the vertex. What's the formula for the vertex? Negative b over 2a. Okay, so -6 divided by 2 is 3. That's outside of my range, so I don't have to worry about it. X equals 3. Okay, so all I have to do is check my boundaries. Maybe the maximum and minimum are at the boundaries. Okay, it's not at the vertex. The vertex is not under consideration. So we're going from 0 to 2. Okay, so I plug in 0. If I put 0 in, I get -2. So f of 0, -2 in the original was 4. F of 0, -2 is 4. We already had that on our list, actually. And then the other extreme is at x equals 2. So if x is 2, y is 0, and f of 2, 0 is 0. Put a 2 here and a 0 here. I get 4 minus 4, which is 0. And this is not a candidate for maximum or minimum either. Okay, so far, the maximum is 4 and the minimum is -1. You can see how long these get. All right, the only other part of the boundary is this, which is -x plus 2. I'm going to think of it as 2 minus x. Okay, it's easier to plug in. And so y equals 2 minus x, and x again goes from 0 to 2. So if I plug in, let's see, along y equals 2 minus x, x squared plus 2 minus x squared minus 2x. But if I multiply that out, it's the same thing, x squared minus 6x plus 4, going from 0 to 2. So the analysis is exactly the same as over here. So I'm finished. So now I can state the absolute max and absolute min. Okay, so the lowest I got was at 1, 0, which was -1. That was from setting fx and fy equal to 0. F of 1, 0 was -1. Then I have a tie for the maximum. F of 0, 2 and 0, -2 are both 4. Okay, so if I could, maybe I'll just sneak in a 4 here and a 4 here. That's the z value. Think of it as the height. and I'm done. Okay, so along the triangle and the interior, where's the absolute maximum? The absolute maximum height is 4 units up. It occurs at 2 places. You want to mention them both. If there's a tie, you should mention them both. And the absolute minimum is at 1, 0, you're 1 unit down. So I drill down into the floor 1 unit, I suppose. Okay, and anywhere else along the triangle itself or the interior, you can get stuff between -1 and +4. So you can see what we're up against in doing these kind of problems. Okay, a lot of stuff. Okay, so I plugged in x equals 0. I plugged in y equals x minus 2. I plugged in y equals 2 minus x, and then I analyze each of those as a single variable. Okay. All right, 33. F of xy equals x squared plus y squared plus x squared y plus 4. -1, 1 cross -1, 1. Cross, these are the limits for x. These are the limits for y. This is not a cross product. Okay. This just means this is where x goes, this is where y goes. You could have another cross and that'll tell me where z goes. So like if it says -1, 1 cross 2, 5 cross 3, 6, this is for x, this is for y, this is for z. Okay, so I get this square here. All right, so what's the absolute max and absolute min? So my boundary, I have to analyze 4 things. X is plus or minus 1 and y is plus or minus 1. Okay, the easy point, the interior. Okay, so find fx and fy, partial with respect to x. 2x, nothing, 2xy, nothing. So 2x plus 2xy, and I'll be setting that equal to 0. Okay, so factor out the 2x, 1 plus y equals 0. That means x equals 0 or y equals -1. Okay, and find fy, derivative with respect to y, nothing, 2y, x squared, nothing. Let's see, where'd it go? Lost my place here. Here. 2y plus x squared equals 0. Okay, it's easier to look at this. X is 0 or y is 1. Okay, now if x is 0, that makes y equal to 0, correct? Remember, both of these have to be true. If y is -1, okay, look at this one. X is 0, y is -1. Put a -1, that gives me -2, right? So x squared is equal to 2, which means x is plus or minus radical 2. And plus or minus radical 2 is not in my picture because radical 2 is about 1.4. So my only critical number is the origin, 0, 0. And what's the function value at the origin? Put a 0, 0, 4. Okay. So the height right here is 4. Okay. That's the easy part. Now the hard part, consider all the boundaries. Okay, so y equals 1. Put a 1 here and a 1 here. That's going to be x squared plus 1 plus x squared plus 4, 2x squared plus 5. It's parabolic. I'm going between -1 and 1. Okay, well, we know what happens, right? The minimum is if I plug in 0, I get 5. And the maximum is if I put plus or minus 1, I get 7. Okay, for that parabola. Okay, so that means I now know this is 7, this is 7, this is 5, but I know that 5 is not a candidate for either max or min. I now know I have 7, 7, 5, 4. So right now, this is the min. These are tied for the max. Okay, y equals -1. Put -1 here, -1 here. Now, -1 squared is 1. If you put -1 here, this becomes -x squared, right? -x squared plus x squared is 0. So I have a constant function, 1 plus 4, which is 5. In other words, f of x, -1 is 5. Everywhere down here, the height is 5. Okay, imagine all of these, the heights are 5. Here it's 4, 5, 7, 7. Okay, now let's analyze x is 1 and negative 1. Okay, x equals 1. X equals 1. 1 plus y squared plus y plus 4. That becomes y squared plus y plus 5. No, the vertex is at negative b over 2a, negative 1 over 2, negative a half. Okay, but f of 1, negative half, we already have x is 1, y is negative a half. So 1, negative a half, back in the original. Put a 1 here and a 1 here, negative a half there, negative a half there. Just grind it out. Okay, you can take my word for it or not. Maybe it's not a good idea to take my word for it since I messed up so much. 1, that's what you plug in for x. And then y was negative a half. So if you square it, it's 1/4 minus a half plus 4. Okay, that comes out to be 4 3/4. So 4 3/4 is no longer, it's not a candidate for maximum or minimum. So I don't have to worry about it. So I'm not even going to bother putting that one down. Okay, and then yeah, I checked the endpoints. F of 1, 1, we already got that as 7. F of 1, negative 1, 1 negative, we already got that as being 5. Okay, so right now I've got 4, 7, 5, 7, all of these are 5. So right now that's the min, these two are tied for max. And finally, x equals negative 1. But let's see, take a look. It's x squared and x squared. So if I plug in negative 1, I get the same analysis as x equals 1, right? So nothing new there. Same analysis as x equals 1 by plugging in. So in other words, I'm not going to get any change for the max and the min. So I'm finished. I have analyzed all 4 sides. So now looking at this picture, absolute max tied here and here, absolute min at the origin. Okay, so I can state my answer now. F of 0, 0 is 4. That's the minimum. F of plus or minus 1, 1, either here or here, it's 7. That's a maximum. Okay, you can see these can get really long. Okay, so everywhere on the inside and the boundary square, if I were to plug in anything else, I will not get 4 or lower, nor will I get 7 or higher. So they're all going to be between 4 and 7, non-inclusive. So this is absolute max. These two are tied for absolute min. Okay. All right, there we go. And now 37 is the last one I was going to show you. I guess I would have done 3 out of the 4. Okay, f of xy is 2x cubed plus y to the 4th, x squared plus y squared less than or equal to 1. Well, that's the unit circle and the interior. Okay. All right, critical points, that's easy. fx, 6x squared. Partial with respect to x. Partial with respect to y, 4y cubed. They both have to equal 0. X is 0, y is 0, right? How do you make that equal to 0? 0. How do you make that equal to 0? 0. Okay, and what's the function value at the origin? F of 0, 0, 0. Okay, so the height at the origin is 0. That's the easy part. Hard part, analyze the boundary. It's a circle. Okay, the boundary is x squared plus y squared equals 1, which means y squared equals 1 minus x squared, correct? That's the equation for the boundary. So I'm going to pick that up, plug it in here. Keep in mind, y to the 4th means y squared squared, right? So here we go, 2x cubed plus y squared, here's y squared, right? Squared. Okay, this is x to the 4th minus 2x squared plus 1 and an extra 2x cubed. Okay, so x to the fourth plus 2x cubed minus 2x squared plus 1, and x goes from -1 to 1. Now it looks like a Calc 1 problem where I'm trying to maximize or minimize this on a closed interval, -1 to 1. That means I have to check the boundaries also at -1 and 1. Okay, so f prime, 4x cubed plus 6x squared minus 4x, which factors into 2x squared plus 3x minus 2. Okay, so this is like Calc 1, maximize and minimize on a closed interval. Okay, do some factorization. This is 2x times 2x minus 1, x plus 2. Okay, so what makes this 0? 0. What makes this 0? 1/2. What makes this 0 is -2. -2 is outside my region, so I don't have to worry about it, right? X and Y are on a unit circle. Whoops. Yeah, I messed up big time here. Okay, so 0 gives me plus or minus 1. Okay, how do I get that? I plug in, right? Y squared is 1 minus x squared, so we put in 0, y is plus or minus 1. And let's see, what else do I have? I have 1/2. Right. So 1/2, you should know on a unit circle, 1/2 gives me plus or minus radical 3/2. Okay, so I have to check this, and check all the boundaries. Okay, f of 0 plus or minus 1. Put a 0. If I put either plus or minus 1, this is going to come out to be 1, right? So 0, 1 and 0, -1 give me a height of 1. One-half plus or minus radical 3/2. Okay, that's a little bit clumsy. Okay, if I put in 1/2, 1/2 cubed is 1/8 multiplied. Yeah, so I have 2/8 plus or minus 3/2 radical 3/2 to the 4th power. Oh boy. Well, if I square it, I have 3/4. Square it again, it's 9/16. So this is 4/16 plus 9/16, which is 13/16. Okay. I'm not going to write it down because the picture will get cluttered up. Okay. Then I check both boundaries. The boundaries are -1, 0 and 1, 0. Okay. Put a -1 here and a 0 here. 0 there, -1 there. That gives me -2. And the other boundary is 1, 0. Put a 1 here and a 0 here. I get 2. And that's everything I need. Okay, so height, think of heights now. 0, 1, 1, -2, 2. So absolute min, absolute max. All right, so f of -1, 0 is -2. That's a minimum. F of 1, 0 is 2. That's the maximum in this particular case. Okay. There we go. Okay, so that's how you do those problems. And now word problems at the end, 41 to 45. How do you do these? Okay, so 41, find the shortest distance from the point 2, 0, -3 to the plane and stuff like that. Okay, so you have a plane in space, and you have a point. Okay, a point. So you want to minimize that distance. Okay, so how do I find that minimum distance? All right, so 41. The point in space is 2, 0, -3. The plane is x plus y plus z is 1. So again, you have a plane, a point, right? So which point in space do I go to on the plane, which will minimize the distance? Okay, so what I do first is change this to z equals 1 minus x minus y. Technically, you could do any of them, but You know, we want to get back to x and y normally, right? We don't want z. So the distance formula is the square root of, right, x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So it's x minus 2 squared plus y minus 0 squared plus z plus 3 squared. But z, I'm going to change it to 1 minus x minus y. So right here, if I put 1 minus x minus y, 1 minus x minus y, it becomes 4 minus x minus y squared. Okay. This is a distance formula. Okay, now you may have had something like this in Calc 1. It's a lot easier to think of minimizing the distance using f of xy is the square of this function. In other words, just drop the square root. Make it f of xy is x minus 2 squared plus y squared plus 4 minus x minus y squared. Okay. Right. The x and y that minimize this will be the same x and y that minimize the square of the distance. Okay. All right, so fx, differential with respect to x, 2 times x minus 2, that's nothing. Chain root, 2 times 4 minus x minus y times the derivative of the inside with respect to x, that's a negative 1. So minus 2, 4 minus x minus y. And yes, I'm going to be setting that equal to 0. Okay, partial with respect to y, nothing. 2y, same thing, chain root, 2 times 4 minus x minus y times the derivative of the inside with respect to y is negative 1. So again, it's going to be a negative 2. Okay, so let's see, what did I do over here? How did I go from here to here? So I think I cleaned up this algebra. Yeah, 2y minus 2y. Let's see, how did I get this? 2x minus 4 equals 2y. I'm sure it's right, 2x minus 4. Oh, I know what I did. Okay, see how this is the same as this? So if I move both of these over, that means these two have to be equal by the transitive property. Okay, maybe another way to look at it is this. This is the same as this, correct? You don't have to do it this way, but this is a sneaky way to do it. It was so sneaky, I tricked myself. So whatever's here and here have to be equal. Okay, this is 0. These two are the same, right? That means these two things have to be equal. Okay, or alternatively, move that over, 2, 4 minus x minus y. This will also be 2, 4 minus x minus y. They're both equal, so they have to equal each other. There we go. So 2x minus 4 equals 2y. Okay, so divided by 2, y equals x minus 2. That's what I did. Okay, so I plugged that into here. 2 times x minus 2 parentheses 4 minus x minus parentheses x minus 2, because that's y. Okay, so I tried to clean that up. 2x minus 4 minus 2 parentheses 4 minus x plus 2. That is 6 minus 2x. So 2x minus 4 minus 2 parentheses 6 minus 2x equals 0. Okay, clean this up. 2x minus 4 minus 12 plus 4x equals 0. And finally, we get something workable. 6x equals 16. X equals 8/3. Y is equal to x minus 2. So 8/3 minus 2 is 2/3. And z is 1 minus x minus y. So 1 minus x, which is 8/3, minus 2/3. That's 3/3 minus 8/3 minus 2/3 is negative 7/3. Okay, so the final answer is the point in question is 8/3, 2/3, negative 7/3 to the point 2, 0, negative 3. Okay, and let me check something else here. Yeah, so this is the point. So you have your plane in space, you have a point. The point that I should aim for is this, but it asks to actually give the minimum distance. So now I have to do the distance formula. okay, from here to here, here to here, here to here. Fortunately, it turns out that all of these are either plus or minus 2/3. Okay, 8/3 minus 2 is 2/3 squared. 2/3 minus nothing is 2/3. And the distance from here to here is also 2/3. Okay. Negative 9/3 minus a minus 7/3 is negative 2/3. So they're all 2/3. So that's 4/9 plus 4/9 plus 4/9, 12/9. Square root of 9 is 3. So the distance is 2 radical 3/3. Okay. All right, so that's 41. And then I was going to show you 45. And then that's it. Then I can give you the last section. Find 3 positive numbers whose sum is 100 and whose product is a maximum. Okay. So x plus y plus z is 100. You want to maximize the product, x, y, z. Okay, that'll happen again when the derivatives are 0. So again, I solve for z. Z is 100 minus x minus y. So f of x, y is x times y times z. And here's z, right? 100 minus x minus y. Distribute 100xy minus x squared y minus xy squared. Okay. And now I find the derivatives. Fx, 100y minus 2xy minus y squared. Fy, 100x minus x squared minus 2xy. Okay. I find fxx and fxy in this case. Now you say, how come I didn't do that over here? Over here, I already knew I was going to minimize the distance. There's clearly no maximum, right? If you have a point in space, right, you can clearly go an infinite distance that you want. So I didn't have to bother. I knew that it was going to turn out to be a minimum. In this case, we're not quite so sure. So we have to go ahead and find a d and so forth. So fxx, derivative with respect to x, is negative 2y. Fyy, derivative with respect to y, is negative 2x. And fxy, how about take the derivative of this with respect to y? That's 100 minus 2x minus 2y. Okay. And similarly, if you try to take fyx, it's 100 minus 2x minus 2y. So it matches. So d, by definition, is fxx, fyy minus fxy squared. So fxx is negative 2x. Fyy was negative 2y. Where'd it go? Where's fyy? Maybe I didn't write it. Maybe I should write it now. Fyy. Fyy. Let's see. Fxx is negative. Oh, I have it right here. Sorry. Right. So fxx fyy is positive 4xy minus the mixed partial squared. Okay, here we are. Okay, so set fx equal to 0 and fy equal to 0. Factor out the y. Factor out the x. 100 minus 2x minus y. 100 minus x minus 2y. Okay, this could mean y equals 0. But if y equals 0, the product is 0. That can't be a maximum, right? Likewise, over here, I could have x equals 0. But if x equals 0, the product is 0. We're trying to maximize the product. The product's only 0, so we know that can't be it. So that means I have to set this equal to 0. I have to set this equal to 0. Okay, so setting this equal to 0, do a little bit of algebra. That means 2x plus y equals 100. And this means x plus 2y equals 100. Okay. All right, so let's see. Multiply this equation by 2. 2x plus 4y equals 200. and then I will subtract up. Okay, that sounds weird, that's allowed. Subtract, if you don't like that, just put that on top of that, and then you can subtract down. Subtract up, 2x minus 2x is nothing. 4y minus y is 3y. 200 minus 100 is 100. So y equals 100 over 3. Okay, if you plug back in, x is also 100 over 3. Let's see. Okay, you can take my word for it, I guess, but if you plug in right here, 100 over 3, 2 times 100 over 3 is 200 over 3, equals 300 over 3. 300 over 3 minus 200 over 3 is 100 over 3. Okay. And then the d, okay, I actually plugged it in. So 4, where's the d? 4xy minus that thing squared. 4xy minus that thing squared. It's greater than 0. Okay, this is 100 over 3 squared. This is 4 times 100 over 3 squared. So it's a maximum. Okay, because fxx is negative. Fxx is negative 2x. Where'd it go? Yeah, it's negative. So I have a maximum. Okay, and it's also easy to show that z is also 100 over 3. Okay, well, you can tell here. Or 33 and a third, right? Maybe I should think of it that way. 33 and a third plus 33 and a third plus what number is 100? Well, another 33 and a third. Okay, so that proves that the three numbers are all 33 and a third or 100 over 3. Okay. All right, there we go. Okay, section 14.8. It's a little bit before 7. Okay, 14.8 topic is Lagrange multipliers. Okay, we're still maximizing or minimizing, but it's subject to some constraint. Okay, let me show you what the problems all look like. Okay, what do we have to do? 3 to 13. So there's 3 through 10, 11 to 13. Okay, you're trying to maximize or minimize some quantity, but it's subject to some constraint. Okay, in other words, look at this, x squared minus y squared. Okay, this clearly has no maximum, x squared minus y squared. You can let x be 1 billion and y is 0. It can be super big. There's also no minimum. You can let x be 0 and y be super big. You can make it as small as you want. But if you're constrained to the unit circle, you can only pick something on a unit circle, then you may very well have a maximum or minimum, right? So this is a constraint. You're trying to maximize or minimize something given a constraint. X squared plus y squared has to be 10. X squared plus y squared plus z squared equals 9. It has to be on this sphere and so on. Okay. So what do we do in those circumstances? Okay, we're going to call this side G. Okay, this is F. This is going to be G. Okay, let me show you a little bit of theory, which you might understand, you might not. If you don't understand it, that's okay. I just want you to understand the algorithm. Okay, so Lagrange multipliers on page 971. Here are some level curves. Okay, f of x, y is 7, 8, 9, 10, and 11. These are the z values. These are the heights. So can you imagine you're walking uphill, right? Height is 7, 8, 9, 10, 11. Okay. Now, if you ignore the blue, you're taking all of the xy plane. Now, however, they're giving a constraint. G of xy is a constant. You have some constraint. So what's the maximum minimum? But you have to be along the blue. Okay. All right. The way they've got it here, it looks like the maximum is 10. Right. I mean, just look at what they got: 7, 8, 9, 10, and then 9, 8, 7. Right. So the maximum here seems to be 10. Okay. So geometrically, what's happening here is that, okay, they give you heights of 7, 8, 9, 10, 11. To maximize f of xy subject to g of xy equals k. This is the constraint. You have to be along the blue. Okay. Then To find the largest value of C such that the level curve intersects K, it appears from figure 1 that this happens when the curves just touch each other. That is, when they have a common tangent line. Okay? They have a common tangent line. Otherwise, if they didn't, you would be able to keep going further. Okay, common tangent, right? Right there. Translation of common tangent, then, or this, next page, means that the normal lines where they touch are identical. If the normal lines are identical, the gradient vectors are parallel. We did that a section back. Okay. In other words, if I take the gradient of f, it's a scalar multiple, which is lambda. Okay, so this is the Greek letter lambda. It's like our L. They use L for Lagrange, the mathematician that came up with this technique. So del f, gradient of f is lambda gradient of g. Del f equals lambda del g. Okay, so one more time, what's happening pictorially is, how do I maximize this? I just go out here, the maximum looks like it's 10, right? Along the blue, 7, 8, 9, 10, okay? I can't go any farther because if I can go farther, then I can get bigger, but I can't. So it just barely grazes here. They have a common tangent line, which translates to identical normals, which translates to gradient vectors are parallel. Okay, so del f equals lambda del g. So in a nutshell, this is what you want. So put this on your cheat sheet. Number 1 on 972. It's really not that bad. And they give you the 3-dimensional version. If it's 2-dimensional, then of course you just drop one of them. Del f equals lambda del g. Okay, lambda is called the Lagrange multiplier. Okay, so to maximize or minimize subject to a constraint, which is what's happening here, it's called the method of Lagrange multipliers. Okay, you do del f equals lambda del g, and g of x, y, z is equal to k. So you solve that system of equations. Okay, again, you evaluate f at all the points that result from this step, and the larger these values is the maximum, and the smallest is going to be the minimum. Okay, it seems all kind of nebulous now, but once I do some, hopefully you'll get the hang of it. Okay, now if you didn't understand any of this stuff that I showed you geometrically, don't worry about it. Okay, what you need to know is you have your f, they give me the f. Okay, it might be 2-dimensional, 3, might be 3-dimensional, 7, it might even be 4-dimensional, 13. Okay, the g is the equation that comes after that. Okay, the thing after the semicolon. All right, so I'll show you how to do that. So you'll find each gradient, the gradient of f, the gradient of g, and you multiply this by lambda. You have a system of equations, and then you solve the system of equations. Okay, so I'll show you that right now. Again, I'll just keep going. I know it's 7 o'clock. I will just do, I think I had 4 problems. Might take me 15, 20 minutes if you don't mind, and then we'll just call it a day, okay? And then that'll be it. And by the way, quiz on Thursday will be something like this. Okay, so take notes, and the quiz will be on this method of Lagrange multipliers, section 8, okay? All right, so I'll show you a 2-dimensional, 3-dimensional, and a 4-dimensional variety. Okay, so number 3, f of xy equals x squared minus y squared, subject to x squared plus y squared equals 1. Okay, so as I mentioned earlier, this is f, this is the g. Okay, so what about the 1? You can ignore the 1. Okay, so g of xy is x squared plus y squared. Okay, so this is the g. Again, notice if I didn't have this constraint, this is a unit circle, right? If I just said you can go anywhere you want in the xy plane, this clearly has no maximum. Let y be 0 and x be super big, goes to infinity, right? let x be 0 and y is super big, that goes to negative infinity. So clearly you have no maximum or minimum. But if you're stuck to being on the unit circle, now is there a max or min? Okay, so here's what you do. Find each gradient vector. So partial of f with respect to x, that's easy, 2x. Partial with respect to y is negative 2y. G sub x is 2x. G sub y is 2y. Okay, so the formula you have is del f, gradient of f, equals lambda, gradient of g. Okay, lambda, Lagrange multiplier. So written as a vector, 2x comma negative 2y, that's the gradient of f, equals lambda times the gradient of g, 2x, 2y. That means 2x equals 2x lambda, and negative 2y equals 2y lambda, right? We just equate coefficients, as it were. Okay, that has to equal that. So 2x equals 2x lambda. Negative 2y equals 2y lambda. Okay, so now my equations become, okay, if I move this over, I have 2x minus 2x lambda equals 0. This gives me 0 equals 2y plus 2y lambda. Okay, so now I just start trying to solve. Factor out 2x. 2x times 1 minus lambda equals 0. That means x equals 0 or lambda equals 1. And I have to analyze each of these separately. How about over here? Y equals 0 or lambda equals negative 1. Okay, so let's try x equals 0. Okay, if x equals 0, put it here. That means y equals plus or minus 1, right? Okay, I plug back into the original equation. If x equals 0, let's see where to go. X is 0, y is plus or minus 1. Okay, how about if lambda equals 1? Okay, so if lambda equals 1, if I put 1 here, negative 2y has to equal 2y. That means y equals 0. And if y equals 0, that gives me x is plus or minus 1. Okay, so right now I have 0, plus or minus 1, and plus or minus 1, 0. Okay, let's see. Lambda equals negative 1. If lambda equals negative 1, if I put negative 1 right here, 1 minus a minus, that's 2. That means x has to be 0. Okay, and x equals 0. Again, I get y is plus or minus 1, nothing new. So I have everything I need. The ordered pairs I have are 0 plus or minus 1 and plus or minus 1, 0. To 4 basic points there, 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 and there. So just find the function values at all of those points. Okay, so f of plus or minus 1, 0 equals 1. Is that right? If I put either plus or minus 1 and a 0, that gives me a height of 1. So plus or minus 1, 0, 1. So this height is 1. This height is 1. And then 0 plus or minus 1. Put a 0 and either a plus or minus 1. That gives me negative 1. That's what I have. Okay, this does get a little bit messy at times, but you just set them equal and it's just some algebra. So I got x equals 0 or lambda equals 1, y equals 0 or lambda equals negative 1. But if I plug back in lambda is negative 1, that means x is 0. I already got that. And from here, if lambda is 1, that forces y to be 0. I already got that. So here, 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 and here. These two gave me 1. These two gave me negative 1. So there is maximum is f of plus or minus 1, 0. That gives me 1. And absolute minimum is 0, is at 0 plus or minus 1, and it came out to be negative 1. I should put an f there, sorry. Should be an F there if I can get an F. Yeah. So the maximum is F of plus or minus 1, 0, that's 1. And the minimum is 0, F of 0 plus or minus 1, which is negative 1. Okay. So that's the way that one works. Okay. All right. So that's a 2-variable one. How about 3-variable? F of x, y, z is 2x plus 2y plus z, subject to x squared plus y squared plus z squared equals 9. That's a sphere, center of the origin, radius 3. Okay. And again, clearly you can see if I didn't have this constraint, if I only look at this, well, you can make that as big as you want. Let x, y, and z be super big. And you can make it as small as you want. Let x, y, and z be big negatives. And that'll be as big negative as you want, right? So clearly no max, no min. But what if I have this constraint? Okay. All right. So new formula, del f equals lambda del g. Gradient of f equals lambda gradient of g. Gradient of f is easy. Partial with respect to x, 2. Partial with respect to y, 2. Partial with respect to z, 1. And the gradient of g, partial with respect to x, 2x. Partial with respect to y, 2y. Partial with respect to z, 2z. All right, so here we go. Del f equals lambda del g. 2, 2, 1 is equal to lambda times 2x, 2y, 2z. Okay, which means, let's see, 2 equals 2x lambda from the x component. Looking at the y's, 2 is equal to 2y lambda, and 1 is equal to 2z lambda. Let me raise it up there. Okay. An easy way to do this is solve each one for lambda. You know x, y, and z cannot be 0. Right? If you put a 0, you get 0 equals 2, can't do it. 0 equals 2, 0 equals 1. Okay, divide this by 2x, divide this by 2y, divide this by 2z. So you get lambda equals 2 over 2x from that one. Lambda is also 2 over 2y from that one. And it's equal to 1 over 2z from this one. That means I can set all of these equal. Okay, so 2 over 2x equals 2 over 2y equals 1 over 2z. It might be easier if you flip them all. Okay, if 2 things or even 3 things, if three can't even say it, 3 things are equal, the reciprocals are equal. So I flip, flip, flip. 2x over 2, 2y over 2, 2z over 1. And I can write 2z over 1 as 4z over 2. And the reason why I'm going to do that is now if I have 2x over 2, 2y over 2, 4z over 2, and they're all equal, just ignore the 2's. That means 2x equals 2y equals 4z divided by 2. So x equals y equals 2z. Okay, x equals y equals 2z. What's that going to make me do is right here, I'm going to put in 2z. X is 2z. Right here, I'm also going to put 2z. That's y plus z squared, right? Okay, so 2z squared plus 2z squared plus z squared is 9. 4z squared plus 4c squared plus z squared. 9z squared is 9. So z is plus or minus 1. That makes y plus or minus 2. And x is also plus or minus 2. Okay, so my choices are x can be plus or minus 2, y is plus or minus 2, z is plus or minus 1. Okay. Now, look back over here. 2x plus 2y plus z. I want to maximize and also want to minimize. It's pretty easy to think about it. Okay. Your choices are plus or minus 2, plus or minus 2, plus or minus 1. How can I make this the biggest? Well, that's if they're all positive. And how can I make this the smallest? They're all negative. Okay, except that I see that I did this wrong. Should be 5 and negative 5. Right? Okay, so one more time, our choices are x can be plus or minus 2, y is plus or minus 2, z is plus or minus 1. How can I make this the biggest? That's if all three of them are positive, the way it's written, right? How can I make it the smallest? Make them all negative. So minimum is f of negative 2, negative 2, negative 1, which is negative 5. And the maximum is 2, 2, 1, which would be positive 5. Okay. All right, I will do a 4-dimensional case and then I'll stop. I actually was going to show you one more, but I can save that for next time, which is number 11. It's a little bit more advanced. Okay, what time is it? Almost 7:15? Okay, so I'll be done in a few minutes. And then, but theoretically, I've given you everything you need for this section, but next time I will do one more problem for you. 4-dimensional one, f of x, y, z, t. But it's actually very similar. F of x, y, z, t is x plus y plus z plus t. X squared plus y squared plus z squared plus t squared equals 1. Okay, this is sort of a hyper-unit sphere. Okay, in 4 dimension. Okay, it's a hypersphere centered at the origin. What's the origin? 0, 0, 0, 0 with a radius of 1. Okay, what does it look like? Well, we can't imagine what's going on in 4 dimensions. We can only talk about it and think about it. Okay, so I showed you a 2-dimensional one, a 3-dimensional one, and now a 4-dimensional one. Okay, it's actually not that hard. Okay, f of x, y, z, t is x plus y plus z plus t. And the g is x squared plus y squared plus z squared plus t squared equals 1. The gradients are very easy. Del f is 1, 1, 1, 1, right? Partial with respect to x, 1. Partial with respect to y, z, and t are also 1. Equals lambda. Partial with respect to x, y, z, and t are also very easy. 2x, 2y, 2z, 2t. Okay. All right, so 1 is equal to 2x lambda. 1 is 2y lambda. So I wrote it like this. 1 is equal to 2x lambda equals 2y lambda equals 2z lambda equals 2t lambda. Solve for lambda. Lambda is 1 over 2x. Similarly, 1 over 2y, 1 over 2z, 1 over 2t. Well, this means x equals y equals z equals t, right? They're all equal. Again, how do you do that? Well, you can do the flipping like I did before. Reciprocate all of them. 2x equals 2y equals 2z equals 2t. Just lose the 2's. X equals y equals z equals t. So they're all equal. If they're all equal, then in my original equation, I can just say x squared plus x squared plus x squared plus x squared, right? X squared plus x squared plus x squared plus x squared. 4x squared equals 1. X squared is 1/4, which means x is plus or minus a half. So my possibilities are plus or minus a half, plus or minus a half, plus or minus a half, plus or minus a half. Okay, and just like the previous problem, if those are my choices, how do I maximize this quantity? If they're all positive. How do I minimize this quantity? If they're all negative. So f of negative a half, negative a half, negative a half, negative a half is -2, and that's a minimum. And the maximum is f of 1/2, 1/2, 1/2, 1/2, which is 2. And there we go. Okay, so I'm done, folks. So theoretically, you have everything you need for the test a week from Thursday, but I was going to go back and show you one more problem, 11, next time, and I know you may have other questions about this, but theoretically, I've given you everything you need for the exam. So next time I was going to do one or maybe two more of the Lagrange multipliers, but then after that, get started with chapter 15 stuff, which will not be on the next test. Okay, chapter 15 is on multiple integrals. So I'll do that next time. And then again, Tuesday of next week, I'll lecture the first half. Second half, I'll let you have for questions and answers for chapter 14. And then next Thursday, the whole day will just be for the exam. Okay, as I mentioned before. All right, so I'm done. If you have a pressing question about something, you can go ahead and bring it up. Otherwise, we'll just go ahead and quit. So no break. The break is we're finished, and that's it. Okay, so does anybody want to ask a question right now, please? All right, so that'll do it for tonight, folks. All right, so that's it. Everybody have a good evening, and we'll see you next time. Okay, bye, everybody.
Thank you very much.
Thank you.
Thank you very
Bye.
much, Professor.
Thank you.
Have a good night.
Professor.
Okay, if I miss you for attendance, put it in the chat now, or send me an email.